Howdy. The purpose of this video is to practice identifying symmetry operations in 2 dimensions and then to practice drawing them on a pattern so we can communicate them to others. So we're going to work with this lattice that appears to be covering a window of some sort. And the first thing that you want to do is to identify your rotation axes of the highest order. And so I can see a 6-fold rotation axis in the middle of here. This is a hexagon, and each element out here gets rotated pi over 3 degrees, or radians, to some other element. So I have a 6-fold rotation axis in the middle of each of these hexagons. I'm going to draw a few of them. And these hexagons are also an excellent place for our lattice points. Now remember, a lattice point is a point in 2-dimensional space that has exactly identical surroundings to any other lattice point. So if this 2-dimensional pattern extended infinitely in all directions, and I was sitting at the middle of this hexagon, I would see the same exact view as if I was sitting in the middle of this hexagon. And it's convention that we put our lattice points, that we let them overlay these symmetry operations of the highest order. So that's why I'm putting them in the middle of the 6-fold rotations, and I'm going to draw this unit cell off to the side. There's rotation, 6-fold rotation, and a 6-fold rotation over here. Okay. So that's one set of rotation axes. What you usually want to do is to keep looking for other rotation axes, and there's a hint in that oftentimes in between these high order rotation axes you'll find other rotation axes. So halfway between this 6-fold and this 6-fold, right here, we have a 2-fold rotation axis. Don't be confused because this looks like a plus sign. Don't say it's a 4-fold because I have to think about each point gets rotated, and that point is not equivalent to this point, right? Because it kind of comes in like a Y here. But it is equivalent to this point over here. So that's a 180 degree or a pi radian rotation, and that means I have a 2-fold rotation axis here. And I'm going to, if I look carefully, I can see that there's a 2-fold rotation axis halfway in between each of these 6-fold rotation axes. And I'm going to draw those on our unit cell as well. And this is slowly going to take shape as I keep adding symmetry elements. Okay, so that's a lot of rotation axes, but it's not all of them yet. If we look in the center of these 3 6-fold rotation axes, I see a 3-fold rotation axis. That is, every point here gets rotated 120 degrees, or 2 pi over 3 radians, to some point here. Again, rotated, mapped to this point here, and rotated again back to the original point. So that gives us a 3-fold rotation axis right in the middle, 3-fold rotation axis right in the middle. Again, the sign for a 6-fold rotation is going to be a hexagon. I'm going to redraw that in case it's not clear here. 3-fold rotation axis is an equilateral triangle. 2-fold is this sort of pointy ellipse. If I had a 4-fold rotation, it would be a square, but I don't have any of those in this pattern. So that is all of the proper rotation axes. I'm going to start looking for mirror planes next. And again, there's a hint in that mirror planes oftentimes lie in the same plane as these rotation axes. So that means that if I start connecting rotation axes with lines, those are really good places to look for mirror planes. And indeed, there is going to be a mirror plane along this axis. Every point here gets reflected down to some point over here. I also have a mirror plane along this line and along this line. And so one way to think of that is if I've identified this one, I can operate on that with the 6-fold rotation axis, and that means there's going to be one here, and one here, where this angle in between of them, all of them, is just pi over 3 radians. So if I draw those on our pattern, we have a mirror plane cutting it in half, a mirror plane along this edge of the unit cell, which is identical to this one. It's just been translated. And a mirror plane along the top, which is identical to the mirror plane along the bottom. Okay, certainly not done yet. There's actually a mirror plane that goes all the way through this pattern. And you know, if you don't see them originally, then a good thing to do is to operate on the mirror plane by the rotation axis. So for example, this twofold here is not going to help us at all. This one is actually, we're not going to be able to get there by operating on the other ones. So I guess we had to find that one ourselves. However, you notice it passes directly through these threefold rotation axes. And that means that I could operate on it and find a mirror plane here and a mirror plane here. So each time I'm rotating that mirror plane by pi over 2 pi over 3 radians. So if I draw those, that's a mirror plane here and a mirror plane here. And so that 6-fold, 3-fold, 2-fold all lie in the same mirror plane. And I would have the same thing down here and the same thing down here. Whew, okay, so that's a lot of mirror planes, but we're actually not totally done with our pattern yet. And the one thing that we have left in this guy is some glide planes. And so if you see, I'm going to draw it on the picture first, a plane that passes through this twofold and through this twofold. And keeps extending outwards, of course. I can consider a point here, gets translated over and reflected up here. Translated over and reflected down here, translated over and reflected up here, and so on and so forth. And so that's what a glide plane is. It's a compound symmetry operation that combines both translation and reflection. And so I have glide planes that actually are connecting all of these twofold rotation axes. Again, these are a little tricky to see. One way to think about it is to think about these 6-folds, right? So this glide plane up here, the 6-fold gets translated and reflected up to this 6-fold, then translated and reflected down to this 6-fold, so on and so forth. And so if I draw these on our unit cell over here, remember the symbol for a glide plane is a dashed line. I have lots of colors at my disposal, but generally these things are printed in black and white, and so you need to have a symbol that's distinct from a mirror plane. And so our glide plane symbol is a dashed line. So that is a lot of symmetry operations, but I still think I'm going to be missing a couple here. So if I look at this twofold, and I have a line, let's see. So this pattern is starting to get pretty covered up. So I'm going to shift down quickly just so we can see these. And we're going to look at the pattern that we would see down here, because it's the same thing to look at. And we're going to think about, again, we have identified glide plane that goes through the twofolds already, and I can extend that one down here. But we might have another kind of a glide plane that connects a twofold up here to the twofold down here. And so that plane is going to lie like this. And again, we can think about mapping this 6-fold, translating and reflecting over to this 6-fold, translating and reflecting over to this 6-fold. So in our unit cell, that's going to be a plane passing this way. And I can see these again in other orientations. So I already identified a glide plane along this plane, but I also have a glide plane along this plane. And I'm going to have another one that starts at this twofold here and lies along this plane. So that's going to look coming out here, coming out here. So I chose a symmetry group that has a lot of symmetry operations to give you guys practice trying to find them all. In reality, once you find a number of symmetry operations, you can usually refer back to the crystallographic symmetry tables for plane groups. Because, for example, once I've found all these rotation axes in the mirror planes, there's only one plane group that has those, and that plane group also shows me where all the other glide planes are. So if I look at the tables, this is the plane group P6MM, and so this notation designates that it's a primitive unit cell. Its highest order rotation axis is a sixfold, and I have mirror planes that are cross bisecting those sixfolds, and there's actually 2 mirror planes per one angle of alpha of rotation, where for a sixfold that angle is going to be pi over 3. So that's why it's mm rather than just m. Okay, so that's it. So that is our space group. I will leave it to you to practice what happens to a general object. Again, the way to think about that is if I have some object that's not sitting on any symmetry operation, what is going to happen to that? And I want to reflect it. And I'll put a comma in it to designate that's reflected. So that's reflected by this mirror plane, but you want to operate on this by all of the different symmetry groups or symmetry elements in the symmetry group. And so again, if you look at the table for P6MM, you will see what that general position looks like.